The really elusive side of physics. We're talking particles that make even neutrinos seem almost sociable.
Yeah, that's a good way to put it.
And you, our listener, you want to get what's happening at the cutting edge, right? Stay informed, but maybe without feeling like you need a PhD first. So let's try and unpack this whole idea of fringe particles.
Absolutely. We're talking about particles that are purely theoretical right now, sitting right on the very edge of what we can actually detect, or maybe even what we could detect soon.
Your sources dig into this kind of twilight zone, yeah.
They do. It's a fascinating area.
So why bother? What makes these hypothetical wallflowers so interesting? Why do physicists even think they might be out there?
Well, it really comes down to the Standard Model, our best theory of particles and forces. It's great, incredibly successful, but it's not the whole picture.
Right. It leaves gaps.
Big gaps.
Right.
Like, what is dark matter? We know it's most of the matter out there, but we have, well, basically no clue what particle it's made of. Then there's the hierarchy problem, this huge puzzling gap between gravity's strength and the other forces, and something called the strong CP problem, the asymmetry the strong force should violate, but doesn't seem to. These fringe particles, they offer potential ways to, plug some of those holes. They could be answers.
Got it. So our mission for this deep dive, figure out what makes a particle practically invisible, and then look at the really clever, almost wild ways scientists are trying to, well, catch a glimpse.
That's alone.
Let's start with that phrase, the border of undetectability. What does that actually mean? What makes a particle so hard to spot, even harder than a neutrino?
Okay, yeah. Think about neutrinos. They're tough because they barely interact, right?
Right. Zip straight through the Earth, usually.
Exactly. So these fringe particles often take those properties and dial them up to 11. We're generally talking about extremely weak interactions. Their coupling constants are tiny, meaning they hardly talk to other particles via the known forces.
Okay, super antisocial.
Yep. And typically no electric charge. So they just ignore electromagnetic fields, which is, a main tool we use to see things.
Invisible.
Pretty much. Then there's mass. It could be anything, really. Some theories predict them to be incredibly light, others super heavy, multi-TV heavy. That makes searching really hard because you don't know what you're tuning your detector for.
Ah, right. So the dial could be anywhere.
Exactly. And finally, for them to matter cosmologically, like maybe being dark matter, they need to be stable or live for a really, really long time. They need to stick around.
Okay. Super weak interactions, neutral, could be any mass, and long-lived. Got it. So let's meet some of the main suspects. First one, WIMPs. Sounds kind of weak.
Yeah, it does. Weakly interacting massive particles. But the name's descriptive. The theory behind them is actually quite strong, especially the connection to something called supersymmetry.
SAHUSY, right.
Yeah.
The idea that every particle has a heavier partner.
That's the one. Supersymmetry predicts a whole zoo of new particles, and in many models, the lightest one is stable, electrically neutral, and interacts weakly. Basically, a perfect WIMP candidate.
And this connects to the WIMP miracle, doesn't it? That always sounded intriguing.
It really is quite remarkable. So if you imagine a particle like this, WIMP interacts via the weak force, has a mass somewhere in the, say, GV to multi-TeV range, so heavier than protons, and you calculate how many would be left over from the Big Bang as the universe cooled.
Okay.
The number you get, the sort of relic abundance, turns out to be almost exactly the amount of dark matter we measure in the universe today.
Whoa. Seriously.
Seriously. It's an amazing coincidence, or, maybe not a coincidence at all. Maybe it's a huge hint.
Okay, that is compelling. So if they're out there, how on earth do you find them? It feels like trying to spot a speck of dust in a hurricane, blindfolded.
It's not far off. The main strategies fall into three big categories. First is direct detection.
Trying to see one directly.
Sort of. The idea is even though they interact super weakly, maybe, just maybe, one WIMP bumps into the nucleus of an atom in your detector, and you see the bump. You see the tiny, tiny recoil energy that the nucleus gets, like a billiard ball hitting another, very gently. Experiments like Xenon, OZ, Pandex, they use huge tanks of ultra-pure stuff, like liquid xenon, deep underground to shield from everything else, cosmic rays, radioactivity.
Right, the noise.
Exactly. And they're looking for these incredibly faint recoils. The challenge is the predicted rate is maybe a few events per ton of xenon per year or less.
Per ton per year. Wow. Okay, that's direct detection. What's number two?
Indirect detection. So instead of seeing the WIMP itself, you look for what happens when WIMPs destroy each other.
Annihilate.
Yeah, if WIMPs are their own antiparticles, which many models suggest, then where dark matter is dense, like the center of the galaxy, or dwarf galaxies nearby,
Uh-huh.
they could annihilate, producing particles we can see, like gamma rays, neutrinos, maybe even antimatter like positrons or antiprotons.
So you look for that smoke from the WIMP annihilation.
Exactly. Telescopes like Fermi-L for gamma rays, IceCube for neutrinos, AMS-2 on the space station for antimatter, they're all scanning the skies for these kinds of indirect signals.
Okay. And the third way?
Try to make them ourselves at particle colliders like the LHC.
Smash protons together really hard and hope WIMPs pop out?
Pretty much. The idea is you smash protons, make a bunch of stuff, and if WIMPs are produced, they'll just fly out of the detector without interacting.
Because they're weakly interacting.
Right. But they carry away energy and momentum. So you look for collisions where the energy and momentum don't balance out, where something seems to be missing. That missing energy could be the signature of WIMPs being produced.
Fascinating. Okay, let's shift gears. Next candidate, axions and axion-like particles, ALPs. Axion sounds like cleaning product.
It does have that ring to it. Well, the original axion wasn't actually proposed for dark matter initially. It was invented to solve a really subtle problem in the theory of the strong nuclear force, QCD.
The strong CP problem you mentioned earlier.
That's the one. A very technical but deep puzzle about why the strong force respects a certain symmetry. The axion provides a really elegant way to explain it.
And ALPs are just similar things.
Yeah. Axion-like particles are sort of a broader category, similar properties, very light, very weakly interacting, but they pop up in other theories, like string theory, and aren't necessarily tied to that specific QCD problem. And both axions and ALPs are now considered really good candidates for cold dark matter.
So what makes them so hard to find? Are they also weakly interacting?
Extremely weakly interacting, even more so than WIMPs, typically.
Yeah.
And they're predicted to be incredibly light.
Lighter than WIMPs?
Oh, way lighter, like millions or billions of times lighter than an electron. Maybe in the microelectron volt to millielectron volt range for the original QCD axion. ALPs could be a bit heavier, but still very light.
Okay, tiny mass, almost zero interaction. How do you even start?
It requires some really ingenious tricks. The main method for looking for axion dark matter is called a haloscope. It uses something called the Primakov effect. The idea that in a very strong magnetic field, an axion can convert into a photon, a particle of light.
Turn into light.
Yep. So experiments like ADMX, they build a resonant cavity, basically a tuned metal box inside a powerful superconducting magnet. If axions making up the dark matter halo are flying through this cavity, and if their mass matches the resonant frequency of the cavity—
By tuning a radio again.
Exactly like tuning a radio. The cavity amplifies the photon signal from the axion conversion, making it potentially detectable as a tiny microwave signal. They have to slowly scan the frequency, tuning the cavity, to search for different possible axion masses.
That is seriously cool, using magnets to turn invisible dark matter into microwaves. What else?
Well, there are helioscopes, looking for axions from the sun.
The sun makes axions.
Theory suggests it could, in its hot core. So experiments like KIAS-T and the future IAXO point a big magnet at the sun. If solar axions stream through the magnet, they might convert into X-rays, which sensitive detectors behind the magnet could then pick up.
Okay, so looking for solar axions turning into X-rays.
Right. And then there's this kind of wonderfully named technique, light shining through walls.
Okay, now that definitely sounds sci-fi.
It sort of is. You basically shoot a powerful laser beam into a strong magnetic field on one side of a thick, opaque wall. The idea is some photons might convert into axions or ALPs in the field. These axions, being so weakly interacting, can just pass straight through the wall that stops the light completely.
Wow.
On the other side of the wall, you have another strong magnet. If any axions made it through, they might convert back into photons in this second magnet. And you have a super sensitive detector waiting to spot even a single photon appearing from nowhere.
That's amazing. Talk about thinking outside the box, or through the wall, I guess.
Yeah, exactly. And finally, like with WIMPs, we can also learn about axions from astrophysics and cosmology, how they might affect how stars cool down or influence the early universe. These can set limits on their properties.
Incredible range of approaches. Okay, next up, sterile neutrinos. The name sterile makes them sound inactive, cut off.
That's a good intuition. So, you know the regular neutrinos, the active ones that interact via the weak force?
Yeah, the ones we can detect eventually.
Right. Sterile neutrinos are hypothetical extras. In the simplest models, they don't interact via any of the standard model forces, except maybe gravity.
Only gravity, why?
But Most models allow them to mix a little bit with the active neutrinos, just a tiny amount.
Yeah.
This mixing allows them to sort of indirectly participate in weak interactions, but very, very feebly. They're like the ultimate introverts of the particle world.
Only talking to the active neutrinos occasionally, maybe?
Something like that, yeah.
Why do we think they might exist? What problems do they solve?
A few things. There have been some persistent anomalies, hints of weirdness in certain neutrino oscillation experiments, especially over short distances. Sterile neutrinos could potentially explain those, but also offer a really neat way to explain why the active neutrinos have mass at all. It's called the seesaw mechanism. A bit technical, but very elegant. And depending on their mass, they could also be dark matter. Not the cold dark matter like WIMPs or Axion, but maybe warm dark matter, which behaves slightly differently on cosmic scales.
You mentioned their mass could be highly variable, too.
Yeah, that's a big challenge. The ones that might explain oscillation anomalies could be around an electron volt, EV, in mass still tiny. The warm dark matter kind might be in the kilo-electron volt, EV range. Some theories allow for much heavier ones, too, so again, you don't know exactly what mass you're looking for.
So how do you search for something like that if it barely interacts and could have lots of different masses?
Again, you need multiple strategies. Neutrino experiments worldwide are constantly getting more precise, looking for any deviation from the standard 3-neutrino picture. That could be a sign of mixing with sterile ones.
Okay, precision measurements.
Then you can look very carefully at the energy spectrum of electrons emitted in certain types of radioactive decay, beta decay. The K-Trin experiment's doing this. A tiny kink or distortion in that spectrum could signal that a sterile neutrino was emitted alongside the electron.
Wow, looking for tiny kinks.
And if KV mass sterile neutrinos are the dark matter, they might slowly decay over cosmic time into an active neutrino and an X-ray photon of a very specific energy.
A single energy X-ray line.
Exactly. So X-ray telescopes look towards places with lots of dark matter, like galaxy clusters, searching for such a faint, monochromatic line.
Hunting for that specific X-ray signature.
And finally, cosmology again. How sterile neutrinos might have affected the formation of the first elements after the Big Bang, or the patterns in the cosmic microwave background radiation. These observations can also rule out certain types or masses of sterile neutrinos.
It's just amazing how many different angles scientists are pursuing. You also mentioned even more exotic things briefly. Graphitinos, Kaluza-Klein particles, hidden sectors. Sounds like deep theory territory.
It is, yeah. These are definitely more speculative, often tied to very specific advanced ideas. Gravitinos are the predicted supersymmetric partners of the graviton, the gravity particle. Their interactions would be incredibly weak, suppressed by the Planck scale, which is the fundamental scale of quantum gravity, so fantastically hard to detect.
Right.
Kaluza-Klein particles come from theories with extra spatial dimensions beyond the 3 we see. Particles moving in those extra dimensions would look like a series of heavier particles to us, a power. The lightest stable neutral one could act like a WIMP.
Extra dimensions.
Right. Yeah.
Wow, and hidden sectors.
That's the idea of a whole parallel set of particles and forces that barely interact with our standard model stuff at all. Maybe only through some very weak portal interaction, like a hypothetical dark photon or dark Higgs. Finding those would need completely new approaches, probably.
So looking across this whole zoo of possibilities, WIMPs, axions, sterile neutrinos, these other exotics, what are the big overarching challenges? What makes this whole search so incredibly hard?
Yeah, the difficulty really is immense. A few key things stand out. First, getting rid of backgrounds. The signals are so faint, so rare, that any other particle interaction, any radioactivity, any cosmic ray could fake a signal or drown it out.
So you need extreme shielding, deep underground.
Deep underground, ultra-pure materials, sophisticated ways to identify and reject background events. It's a constant battle.
Okay.
Second, you just need extreme sensitivity. That often means building huge detectors, tons, sometimes kilotons, to increase the chance of an interaction. And being able to detect incredibly tiny amounts of energy, so very low energy thresholds.
Bigger and more sensitive.
Right. Third, you often need totally new detection ideas. You can't just use standard particle physics techniques. You have to invent methods tailored to the specific, often unknown properties of the particle you're hunting. Like the Axion haloscope, that's a perfect example.
Tailor-made experiments.
Exactly. And finally, the scale. These are huge, often global collaborations. They take enormous amounts of funding, hundreds, sometimes thousands of scientists and engineers, and decades of work. It's a long, long game.
It really highlights the dedication, the sheer ingenuity involved. So we've taken this deep dive now into these nearly invisible particles. What's the bottom line? What should we take away?
I think the main thing is that this search, it's pushing the absolute limits of experimental science. It's incredibly challenging.
But the payoff could be huge, right?
Oh, immense. Finding any one of these particles would be revolutionary. It could solve the dark matter mystery, explain neutrino masses, maybe point towards a deeper theory beyond the standard model. It would fundamentally change our picture of the universe.
That WIMP miracle idea, for instance, the amount of dark matter just happening to match the calculation for these hypothetical particles.
Exactly. That kind of connection, if it's real, is profound. It suggests we're on the right track, that there's a deep logic linking particle physics and cosmology that we haven't fully grasped yet.
And even if these searches find nothing, if the WIMPs aren't there or the axions remain hidden, is that still useful?
Absolutely. No results are vital. They tell us where not to look. They rule out theories, constrain possibilities. If WIMPs aren't found down to a certain sensitivity, it makes other candidates like axions maybe look more likely or pushes theorists to think about new ideas. It guides the next generation of experiments. It's all part of the scientific process.
Okay, so as we wrap up this dive into the universe's hidden corners, maybe here's something to chew on. Just think about how much of reality might still be completely invisible to us, even with all our amazing science. Our current understanding feels pretty complete sometimes, but what if it's just scratching the surface? What would a truly undetectable universe, full of stuff we just can't perceive, even mean? What does that say about existence, about the limits of what we can ever know?
It's a big thought.
It is. It's a vast unknown out there, and the chance that something totally unexpected is lurking just beyond our reach.
Well, that's pretty exciting, isn't it? Thanks for joining us on the deep dive.